think we can start. Let me run application. Okay. All right. So hello, everyone. Welcome. Hope you're doing well. Welcome to this workshop series on artificial intelligence. Today is going to be the second course, which is the deep learning course. But again, we're diving into the course. Allow me to introduce myself again, just in case there are new participants. So my name is Abdelghafour HALIMI. I have a PhD in image processing and artificial intelligence from the National Institute of Toulouse in France. And I was working as data scientist for worldwide companies. And I have over a decade of experience in the AI field, working for several projects for different fields. And I recently joined the Chaos Visualization Core Lab. So our Core Lab provides a lot of facilities and expertise in various fields, like 3D data visualization, virtual reality, data science. So don't hesitate to contact us. I put you a link here for our wiki page where you can find more details and information about the different services that you are providing. You can check also our YouTube channel, where you can find the previous tutorials and training provided by me and my colleagues. All right, let's start by a brief summary and some key points of what we have already covered in the last course. We have seen the meaning of machine learning, right? Machine learning is using an algorithm or computer program in order to learn some patterns in the data, and then using that algorithm and what it's learned in order to make some prediction on the future on new similar data. We have seen also the difference between traditional algorithm and machine learning algorithm. Traditional one gonna start with an input and a set of instructions in order to get the output. On the other hand, machine learning gonna start with an input and an ideal output, and they're gonna try to figure out the right instructions, right? We have seen also when we shouldn't use machine learning. If you can build a simple rule-based system, go for it. This is the best model that you can have. Forget about machine learning. It's a waste of time. Actually, it's rule number 1 of Google's machine learning handbook. All right, now, what is deep learning? I mean, deep learning is a buzzword right now, right? But in reality, it's just a type of machine learning. We're going to use neural networks to learn these patterns. Let's see a small example. Where normal machine learning algorithm gonna use some statistical methods to learn these patterns. For example, if you take this example, if you want to predict from this image if a person is a male or female, machine learning algorithm gonna start by extracting some features, maybe the roundness of the face, or the distance between the eyes, or the distribution of the pixel intensity of the image, and you're gonna then use these features to build a classifier like support vector machine, random forest, logistic regression, in order to predict if it's a male or a female. Deep learning gonna do exactly the same thing, extracting the features and doing the classification, but this time in an automatic way, using neural networks. Again, I'm not gonna enter into the mathematical details behind this. You can see it as a black box. We're gonna do the job of learning these patterns using neural networks. Another illustration of it, you can see it as artificial intelligence is going to be a type of advanced technology that mimics human intelligence or behavior. Machine learning is going to be a subset of AI. We're going to use statistical methods to learn the patterns from analyzing the data. And finally, deep learning is going to be a subset of machine learning that use neural networks to learn these patterns. Okay. Now, why should we use deep learning? I mean, good reason could be, why not, right? But of course, better reason. For a complex problem, can you think of all the rules? Probably not. I mean, if I'm asking you right now to do a self-driving car, can you think of all the rules? It's impossible. It's going to take you years. Deep learning can do it. This is why deep learning is very powerful. Now, there are many other reasons where deep learning is good for. you can see that he's good with problems with long list of rules. Again, when the traditional approach is going to fail, deep learning may help. When your environment is continually changing, deep learning is very good at adaptation and learning new scenarios. And finally, when you're working with a large collection of data, right? I mean, again, can you imagine trying to handcraft rules of what 100 different kinds of flukes looks like? Again, it's going to be very difficult for you. Now, there are where deep learning is not typically good for. Let's see some examples. When you need explainability, this is the problem with deep learning. I mean, the patterns learned by deep learning are very difficult and not interpretable by a human. This is the problem with deep learning. I mean, if you look at the previous examples of machine learning, the patterns are like something that a human can understand. Distribution of the pixel intensity, like the roundness of the face, the distance. The patterns learned by deep learning are not understandable by a human. This is a very big problem, explainability. Then, when the traditional approach is a better option, again, if you can use and accomplish what you need with a simple rule-based system, go for it. It's exactly the same thing like machine learning. This is the best model that you can have. Forget about deep learning. When errors are unacceptable, again, deep learning models are probabilistic models. They're going to give you some probabilities. So if you are working with subjects that must not have errors, forget about deep learning, because at least it's going to give you a small error. It's probabilities. Then, when you don't have much data, again, deep learning models usually require big amount of data to produce great results. Now, here, again, not a rule, just in general and by experience. In general, when you are working with structured data, CSV files, tabular data, Excel files, machine learning algorithm tends to be working the best. When you are working with unstructured data, like audio files, images, text, deep learning models tends to be working the best. Not a rule, just keep it in mind. Now, here I selected some of the deep learning most common use cases. We're going to find recommendation systems that are the one used in YouTube channels or Netflix. We're going to find some translation, speech recognition, computer vision in order to detect some objects, natural language processing, like the large language models, ChatGPT and others. And finally, it's also adapted to do some classification and regression. Now, we're going to try, I said again, try to run a live demo. Again, I don't promise anything, I don't guarantee anything. You know how it goes with the live demos. Let's try to run it and see if it's going to work. Of a computer vision example. Okay, let's see. At least it's doing something, which is great. All right, this is running on my own local machine, a computer vision one. You can see that not only he's doing the object detection, the classification, but he's doing also the segmentation, which is amazing, right? You can see it here. It's looking very good using my webcam. Now, let's try to take it a step further. Let's see if we can do this. Amazing. Now it's working with my phone. So it's wirelessly doing the computer vision algorithm is working wirelessly, which is amazing because now this kind of stuff, you can see how he's performing. He's performing very good. You can see this now that it's working wirelessly and detecting the object and everything. Now it can be integrated with drones, for example, to resolve some problems. And this is running locally with my machine. So it's amazing, as you can see. All right, at least it worked. So it's amazing, perfect. This is a small example of what you can do with deep learning for computer vision. Now, I mean, this is cool, right? It's amazing. But quick aside, sometimes deep learning can be very dangerous. I want to warn you about this, to be careful using deep learning, because sometimes it can be very, very dangerous. Why? Because sometimes you can diffuse fake news, for example. How? Using deepfake. Here, I'm going to show you a small example of a deepfake. And you can see that it's very dangerous. You see how it performs just by running. You have some knowledge on AI, you can do this kind of stuff. On my office, just by running this, giving him some pictures of Elon Musk, Ryan Reynolds, Einstein, I was able to do this. And you can see how it's performed, very good. I didn't push the algorithm very hard. And I was able to get this kind of results. So you can see that's very scary, right? The problem that it can be even scary. This was a recorded video of me. Now this kind of stuff can be run on live stream now. So you can, for example, chat and discuss with a guy like Elon Musk, and it's not Elon Musk, you know? This is why it's very, very scary. This is a small, quick side of the dark side of AI. I want you to see this kind of stuff. All right. Okay, now here I selected some of the common machine learning algorithms that we have already used in the previous examples. You can find random forest, live Bayes, support vector machine, and some common deep learning algorithms like neural networks, fully connected neural networks, convolutional neural networks, recurrent neural networks, and finally transformers, and many more. And depending on how you're going to represent your problem, many algorithms can be used for unstructured data and structured data. Today, we will be focusing only on neural networks, fully connected neural networks, on other words, deep neural networks, and finally convolutional neural networks. We're going to use TensorFlow for this. So what are these neural networks? This is a small example of an anatomy of neural networks. You're going to have what we call an input layer. This is where the data goes in. Here, it's represented by and composed by two neurons. We call this neurons, neural units, or non-units, neurons, or yeah, this is exactly how we call it. We call them. So the data goes in here. Then you're going to have what we call a hidden layer. This is where the model is going to learn the patterns. Well, this is very important because here, for example, it's a small neural network with one hidden layer composed of 3 neurons, but it can be a very complex one and big one with hundreds of hidden layers with hundreds of neurons. And finally, you're going to have what we call an output layer, which is going to represent the learned representation or the prediction probability. Here is a small example. When you are working with unstructured data, like images, text, or audio files, first step, you need to do some numerical encoding in order to be understood by deep learning models. Then you're going to choose the appropriate neural network for your problem. And here you're going to learn the patterns. And finally, you're going to have representation outputs, which are going to be represented by a matrix of prediction probabilities, right? And then you're going to finally convert it into something that a human can understand. For example, if you are working with images, is this a ramen or spaghetti? Or if you are working with a tweet, is he talking about machine learning or deep learning? Audio files, you're going to do some speech recognition to transcribe this. This is an example of how you can use it. Now, okay, just to give you an idea what's going on inside the neural nets. This is a small neural network with 1 neurons. It's going to be the same thing for each neurons. And this is how you're going to learn these patterns. Just giving you an idea, right? So you're going to have the input, which is represented by x. And then for each neurons, you're going to have z of x and a of z. Z of x is going to be equal to wx plus b, which is going to represent the model that you are working on. W and b are going to be representing the parameters of the model. We call this also the weight of the model. Then you're going to have the a of z, which is called the activation function. Here it can be equal to sigmoid or rectified linear unit or linear function. It depends on the problem that you're working on. And it's going to give you the y hat, the prediction. So going from x to y hat, it's called forward propagation. Now that you got your prediction, the y hat, you want to fix what we call loss function or cost function. It can be mean squared error, mean absolute error. I mean, you're going to fix an error between your prediction and the true value, the y hat and the y. And you're going to try to minimize this, right? By using some optimization methods like the gradient descent. And you're going to update these parameters, this weight, w and b, until it converge. These steps, it's called backward propagation. Again, this just give you an idea. We don't care. Let's move on. So here, these are the main type of deep learning problems, like we have already seen this: supervised learning, unsupervised learning, reinforcement learning, and transfer learning. Today, we'll be focusing on writing some codes on supervised learning and transfer learning. Now, for supervised learning, these are the main inverse problems used: regression, classification, computer vision. Today, we will be focusing on creating some examples on these: some regression, some classification, and computer vision examples, but using this time neural networks. So we're going to start with the first one, regression with neural networks. We have already seen this. Regression, what does it mean? Trying to predict a number. For example, how much this house will cost, or how many people will buy this app. But sometimes, if you are working with computer vision, as we have already seen, you're going to be resolving what we call a bounding box. Here, this is the regression problems. You see here, in the corner left here, these coordinates, 13 and 90, were predicted by resolving regression problems. You see? So it can be combined with computer vision also. Now, if you take an example of predicting the house price, for example, the first thing that you need to do is build in your model, right? So you're going to need some inputs and outputs. For the inputs, here for your house, you're going to find 4 bedrooms, 2 bathrooms, and 2 garages, for example. This is going to be the inputs for your algorithm. But before, you need to do some numerical encoding. We have already seen this, the 1-hot encoder, for example. Then you're going to have the output, which is going to be the predicted price. And this comes from looking at a lot of examples of this. So you're going to train on this lot of examples here, and then you're going to do the prediction. Now, the input and the output shapes are very important. So here, for example, you can see that the input shape is equal to 3 bathrooms, and garage. And you're going to represent this as a tensor. And the shape of the output is equal to 1, because we are predicting the price. Here, I selected some of the common regression evaluation metrics that you're going to find: mean absolute error, mean squared error, Huber, or R2 score. We're going to see this later in Jupyter Notebooks. Now, neural networks with classification. Again, classification problems is when you're going to try to predict if something, one thing or another. For example, is this email spam or not? If it's only 2 options, it's called binary classification. More than 10 options, multi-class classification, like is this patient healthy, having heart disease, or having tumor, for example. Sometimes you can find also what we call multi-label classification. For example, what tags should be used for this article to have, like, for example, machine learning, representation learning, artificial learning. This is the kind of problems that you are using when working with classification problems. Now again, if you take an example of medical patient records, first thing that you need to do when you're going to try to build your deep learning algorithm, you need some inputs. In our case here, it's going to be represented by these parameters: the weight, the sex, the heart rate, chest pain. But before, you need to do some numerical encoding for them. And finally, you're going to have the matrix of the probabilities for each patient, as you can see here. And this comes from looking at a lot of examples of this. You should remember these steps, because it's going to be exactly the same thing when you're going to build your own models. And the shape is very important here. In our case, it's equal to 5. Why? Because we have ID, the weight, the sex, blood pressure, and the chest pain. And for the final result here, the shape is equal to 3, because we have 3 Ks that we want to predict. This is the metrics that you are using on classification. You're going to find accuracy, precision, recall, F1 score, and confusion matrix. And finally, convolutional neural networks for computer vision. Now, computer vision means only that you are working with images. Here you can find some of the common one. Binary classification is this image representing steak or pizza. If you are working with class classification is this photo representing sushi, steak, or pizza, for example. And finally, object detection, what we have already seen in the live demo, right? And here you are resolving two inverse problems, a regression one and classification one. A regression one to predict the bounding box, which means the coordinates, and the classification one to predict like this class this object belongs to which class, cat or dogs. So we are combining two inverse problems in one, regression and classification. Now again, if you want to build an application for food to see different kind of food, to detect this and to predict this, you're going to need a deep learning model for that. So you're going to need some inputs. Here you are working with images. So you're going to have the size of the image, width and the height, but you're going to have also what we call color channel, RGB, here. And again, you need to do the numerical encoding each time. Here, for example, we are normalizing these pixels. And you're going to find the output, which is going to be the matrix of the prediction. And it's going to be coming from looking at a lot of examples of this. We're going to try to build this up later in Jupyter Notebooks. But again, here what's important, as we are working with images, the most often one, like the used one, is the convolutional networks, not the artificial networks, because it's optimized for this kind of stuff, working with images. Again, the shapes here, it's going to be a little bit different. You're going to have the size, the width, and the height, and the color channel, but you're going to add what we call the batch size. Remember when we were working with thousands of images, 70,000 of images? It cannot be fitted in the memory of their PC, so you need to give them a subset, here 32, and you're going to go through the whole data. This is the input of your algorithm, and the shape of the prediction is going to be equal to 3 here, for example, because we are predicting 3 kind of food. All right, we're going to try to do this using TensorFlow. It's a library that represents end-to-end platform for deep learning. It's in Python. It's make us able to access many pre-built deep learning models. It gives you the whole stack, which means going from pre-processing the data, modeling the data, and deploying it as an application. And finally, it was originally designed and used in-house by Google. We're going to use this library. Now, why? Because it's easy to build on it and deploy it for the production. But the most important part, it's compatible with GPUs and TPUs. This is very important, because it's going to allow us to accelerate our learning. GPUs is very important when working with deep learning models. All right, what we're going to try to cover today. We're going to try to go through these different steps. First thing is getting the data ready. For that, we're going to turn all the data into numbers. Neural networks cannot handle images. Make sure all of your tensors are the right shape, and finally scale them, which means normalize them, because neural networks tend to prefer these normalizations. Then we're going to try to build, train, and evaluate our model. This is an example of it. Let's see this in details. You remember this schema here? This code is representing exactly this schema, 1 neurons. So the first step is, of course, to construct your neural nets, or maybe using or importing pre-trained one. We're going to see this for transfer learning, for example. But here, we are constructing this schema. So as you can see, we are using 1 layer with 1 neurons here, as you can see here. And then we're going to use this part to compile the model, which means prepare it to be used with the data. Here you're going to find 3 important parameters. The loss function, you remember, the one that you want to minimize. Here it's equal, for example, to mean absolute error, as you can see. Then you're going to have the optimizer. Which one do you want to use to minimize this loss function? Here it's equal to SGD, which means stochastic gradient descent. And finally, the metrics, mean absolute error, to see a human interpretable values for how well your model is doing. Then you're going to fit it, which means train it. Here, you're going to put some epochs, which means how many times the model will go through the whole training examples. And finally, you're going to evaluate it using these metrics. Here, it's equal to mean absolute error. Now, this is an example of that represent this schema, 1 neurons. But when we are working with regression, this is the kind of models that you're going to use. You see here, if we are working with here 3, the shape is 3 parameters. It's going to be here equal to 3, for example. And then here, you're going to have the hidden layers. For example, here it's 3 hidden layers with 100 neurons for each hidden layer. So it's a big one. And this, what you need to know for the moment is that for regression, you're going to have for the loss function mean squared error or mean absolute error. And for the optimizer, either SGD, stochastic gradient descent, or ADAM, for example. This is the most common one used for regression. For classification, but before we go this, it can be either simple, again, a simple neural networks, like with 2 hidden layers and 4 neurons, or it can be very deep and very big, as you can see, 100 of hidden layers and 100 of neurons. Classification is going to be exactly the same. If you are working for images here, for example, the shape going to be the size of the image and the color channel, RGB. But what you need to remember here is for the loss function, if you are working with binary classification, in general, we are using for the loss function binary cross entropy. And if you are working with multi-class classification, we are using categorical cross entropy. And for the output activation, we are using sigmoid for binary classification and softmax for multi-class classification. This is what you need to know for the moment. And the others parameters are the same, like the regression one. Now again, it can be either a simple one or very deep one. And finally, the architecture of convolutional networks. Now this is a complex one and bigger one, but you can see it as it's going to be the same as artificial neural networks, but you're going to add some layers before that represent the convolutional layer with a lot of filters. And you can see it as this. This is a small example of it. You're going to have the image, the RGB, and you're going to do the convolutional layer who's going to like try a lot of filters on your images in order to get some, maybe, the edges of the images or the texture of the images. You need to learn some information about these images. Then you're going to use what we call max pooling, which means just reducing the size of the matrix. And you're going to repeat this if you want something very deep, like this one. Doing a convolutional layer, then max pooling to reduce the size, you see, from 32 to 16, then doing same thing, convolutional one, and then max pooling to reduce the size. And finally, you're going to flatten this into a layer, and you're going to use the artificial neural networks. And it's going to give you very good results. We're going to see this layer. Now, these are the most popular and useful computer vision architectures. So you have ResNet, EfficientNet, or MobileNet. We're going to try to use this, but this time for transfer learning, because they are already pre-trained models. OK, next step is to improve our model, right? For that, these are the different steps that you're going to need to do. Again, this is a small model, as we have seen, with 1 hidden layer and 1 neurons. And this is a larger model. So how to improve this one? Maybe by adding layers, like this one, 3 here, by increasing the number of hidden units, which means the neurons, from 1 to 100. Maybe by changing the activation functions. Here it's equal to rectified linear unit. By changing the optimization function, changing the learning rate here for the optimizer, and fitting for more data and for longer. This is the kind of stuff that you're going to do to improve your model. And again, we want to avoid overfitting. Remember, last course, student who learned only from the final exam, he didn't learn anything. He's just doing memorization. This is exactly what you want to avoid, memorization. We want our model to be general. So we want to avoid overfitting. We are looking for this, the optimal fitting here. For that, these are some fixes. You can, for example, get more data and better data, which is difficult when you are working in a real world. Use transfer learning when you are able to do it, if there are some pre-trained models for that. Or doing some data augmentation. What does it mean? You're going to take your original image, and you're going to do some stuff on it. Rotate it, shift it, Zoom in it. Why? To make it very difficult for the model to learn. That way, you're going to avoid a little bit of overfitting. Some helpful tips before we finish. Again, 3 sets. Remember, this is the same thing for deep learning. The training, validation, and test split. It's very important to run our model to be general, to perform very well on data it hasn't seen before. Then you need to visualize each step. We're going to see this. We need to visualize. You're going to get some insight by visualizing each steps. And finally, of course, experimentation. You need to experiment by yourself and a lot, by doing a lot of things on the models. You're going to see this. And that's it. All right. Thank you, and let's start modeling. OK. I'm going to try to go through the different examples that you have seen. Regression, classification, and computer vision using neural networks. So for that, for those who want to do it, you can already find everything here in the GitHub repository. So again, the same thing. You go to the GitHub repository. You're going to find different folders. You go to the deep learning one, and you're going to find the different Jupyter notebooks in English and Arabic. And if you want to practice right now, you can have access to the Class Hub. So for that, you need a GitHub account. Either you create one or you already have one. You go to this link, put your name. If you already did it last time, you don't need to do it. And then you go to the Class Hub and run the Jupyter Hub here. And you can follow with me. Otherwise, you can just watch, and I'm going to go through the different examples. So we have 3 Jupyter notebooks for that. Let's start with the first one, which is regression using neural networks. OK. OK, so the idea here is that we're going to try to go through these different steps of our architecture of a regression model, creating a synthetic data first to work on it and to understand the principle behind this. And then we're going to try to run on real examples and going through these different steps here, creating the model, compile it, and fit it, and evaluate it at the end. Again, this is the typical architecture of regression neural networks. We have already seen this. And let's start by creating a small example of it, of synthetic data. Here, we're going to create a linear function. As you can see, we have our x and y. It's represented like this. It's a linear function, right? Y equal to x plus 10. As you can see, it's easy for a human to get this, right? It's easy for us. But you're going to see that for deep learning, it's a huge task to get this. Yeah, it looks like it's easy, but for a deep learning, when you're going to start doing a lot of building models, you're going to see. Again, just to give you an idea, when you are working with some shapes here, we call this a tensor. So for that, here it's going to be equal to shape 3 if you are looking, for example, to predict a house price, bedroom, bathrooms, garage. So you're going to use 3 parameters to predict 1. In our synthetic data, we're going to use 1 x to predict 1 y. So it's very hard for deep learning to get this, because we are going to use only 1 element here, as you can see, 1 x to predict this. All right. Let's start by building the first model, all right? Creating our model, compile it, and then fit it. For that, we're going to use the one that you have already seen in the presentation, right? 1 neurons. We're going to use only 1 neurons. And we're going to use the mean absolute error for the loss function, and for the optimizer, the stochastic gradient descent. And we're going to give him the x and y to train on them and see if they're going to perform well or not. For 5 epochs. OK, it's going to give us some results. Let's see the results. If you want to predict for 17. Now we know that the answer is going to be 27 for us. It's a linear function, so it's easy for us. Let's see how we're going to perform. 24. You see, it's not that good. Just by 1 neurons. Let's try to improve this model. We have seen this by adding a lot of layers, increasing the numbers, changing the activation function. Let's try to go through this and see if it's going to perform well. First thing that we need to do, for example, keep the same model and add more epochs, which means you're going to train a lot. What do you think? You're going to perform very well or not? For 100 epochs this time, not 5 epochs. Okay, now you can see it from the mean absolute error. Not that good, right? If we predict for 17, it gives us now 30. We know the answer, like it's 27. It's a little bit better than 24, but it's the same thing. It's not learning anything. Okay, so you can see that it's difficult for him, right? I want you to know here, this is the kind of stuff that you're gonna do by yourself. Building a model, evaluate it, try to tweak it, try to change this, evaluate it again, build another model, try it. This is the kind of stuff that you're gonna do when working with deep learning models. This is an idea just to give you how you can work on it. Now, let's try with bigger and more samples. Let's take 50 samples this time. For x and y, we know how to create this, right? Y equal x plus 10. Plus 10, all right? So if you wanna create a model for that, we're gonna try to create some training set and validation set and test set. But again here, we're gonna do only the x train and the x test. We're gonna take 40 samples to train on them and 10 to test. Okay, now we have our data. Let's visualize it. Okay, this is what we wanna do. We have our training data here and the test. We wanna predict this. Again, let's see how we're gonna perform using the same kind of models. The first one, we have seen that it didn't perform well. We're using 100 epochs. We're gonna using the same models. But by visualizing this, it's gonna be better, and you're gonna have better idea. Again, if you wanna visualize your model, you can do model.summary. Here, it gives you the number of parameters of your model. It's equal to 2. Why? You remember this schema? We have only 1 neurons, so we have only 2 parameters, W and B, the weight. This is why it's equal to 2. If here, for example, we change our model and give him 2 DENS, which means 2 neurons, the number of parameters of our models is gonna be equal to 4. Right? Okay, now let's visualize how he's performing on the X test. Again, we're gonna use model.predict. You have already seen this for the machine learning course. It's the same thing. It's gonna give you the prediction. And if you see it, if we plot this, okay, now we have a better idea how he's performing. You see, very bad. Exactly. You see, this is why I was telling you that it's easy for us, but for him, it's very complicated because you are giving him only 1 and you want to tell him to predict this. You don't know what is a linear function. He's trying to learn some patterns to predict this. So again, let's try to evaluate this prediction. Again, here you can use either mean absolute error, because we are working with the regression problem, or mean squared error. And you can see that it's equal to 30 here, in our case. But I'm giving you some function that you can use from TensorFlow to do this. You can use this function mean absolute error or mean squared error. It's already there. And it's going to give you a better idea of how your model is performing, right? Let's create a function for it. That way it's going to be easy for us to evaluate. And this is the kind of stuff that you're going to do. Run an experiment to improve your model. Let's try to build these 4 models and see if you can resolve this problem with a linear regression, right? Let's see. We're going to start by the same original model, 1 layer trained for 100 epochs. Then we're going to try another one 2 layers this time, trained for 100 epochs. Then we're going to try 2 layers for 500 epochs. And finally, the most advanced one, 3 layers, more neural nets, I don't know, we're going to use a lot, and trained for 100 epochs. Let's see how we're going to perform. The first one, we have already seen this with 100 epochs, right? Not that good. The prediction is in red, is not performing very well, right? And again, you can now, with the function that you have created, get the mean absolute error and the mean squared error. It's very huge, very big. The second model, we have said that we're going to try to add a new hidden layer this time. So instead of going only with 1 neurons, we're going to go with 1 neurons and 1 neuron, so 2, with 100 epochs. Okay? Let's try. Okay, you see? Now he's kind of learning some stuff. Okay, this is good for us. So by adding some complexity to the model, he's trying to learn new things. Now, by seeing this, you're going to say maybe, again, you're going to calculate this. Let's try to run it for more epochs. 500, maybe he's going to learn more, right? So you're going to take this same model with one hidden layer of 2 hidden layers, and you're going to run it for 500 epochs this time. Maybe he's going to learn more, right? Get better results. You see that it's even worse. Why? Maybe he's doing overfitting. This is you see, you let him learn a lot. This is overfitting. So he learned a lot. He didn't get any idea. He get lost. All right. Now, if you look at the mean absolute error, mean squared error, same thing. It's gonna be huge. Let's try now to go deep and use these kind of models. 3 hidden layers with 200 neurons here, 200 neurons and 100 neurons here. So it's a big one, right? And for 140 epochs. Let's see how he's gonna perform. Is he gonna get it or not? Amazing! you see what kind of stuff we did in order to just predict linear regression, linear function. You see, now you get it. If you look at the different mean squared error, it's amazing, 0.5. All right. Okay, now you can compare the different results. So I want you to know that this is a small example on synthetic data to see how for deep learning the patterns are not the same as us. He have his own patterns, so you need to play with it. This is the idea. Again, now you can save your model, of course, and load it again. I give you some function for that. You can use already the default one or this one, and you can load it again, and you're going to find your model when he's learned. So again, Jupyter Notebooks, you can find this all on my GitHub, so you're going to practice by yourself again. This just gives you an overview. Yeah. So, sorry? Yeah. Maybe you're going to get an overfitting. This is why it's difficult to, this is why I'm telling you, the experimentation is very hard. Exactly, yeah. You need to experiment by yourself. But there are some techniques to avoid this overfitting things. To stop early, for example. There are some functions for that, specific to that. But here I'm going to give you an overview of all this, right? Okay. Now that you have saved our model and loaded it again, you can find the same results. Let's try now to move to a real world examples, a larger one. Here, we're going to use what we call a medical cost data set. So it represents medical insurance for individuals based on number of different parameters like the age, sex, BMI, children, smoking status. And it looks like this. It's a data frame, CSV file, and it's looking like this. So we have, again, some categorical features. You remember, the sex, female or male, smoker, yes or no, the region are categorical features, right? And you're going to have some numerical one. And you will predict these column, the charges. So here you're going to find some information about our data. You can see that we have 1,338 samples. And for that, again, we have already seen this, how to get rid of the categorical features. We're going to use the panda get dummies. It's going to convert this with one-hot encoding. You can see that it's converted to numerical one. And the idea now is to split this into X and Y, right? The features and the target label. So for that, you're going to drop the charges, this column here, because this is what we want to predict. And we're going to have our X and Y, right? Now, next move is to split our data into some training and test. We're going to use the scikit-learn one. The same thing. We're going to take, for example, 80% for the training and 20% here for the test size, 20% for the test. All right. Now we have our X test and X train. OK. Now we can start building some models to predict this. Let's try to see how it's going to perform. This is our first insurance model, right? We're going to start the same thing. 1 neurons here, and two hidden layers with 1 neurons each. Let's see how we're going to perform. All right, you can see that for 100 epochs, the mean absolute error is huge. So it's not performing very well, right? Yeah, it's very big. All right, let's try now these 3 kind of stuff. Increasing the number of hidden layers from 2 to 3, increasing the number of units for each one, and changing the optimizer from stochastic gradient descent to Adam algorithm. Let's see how we're going to perform, for example. So here, we're going to take 2 hidden layers, one with 100 neurons, here 10 neurons. We're going to change the optimizer from SGD to Adam and 100 epochs. Again, let's see. Now it's going to start taking long time. Again, this is when we're working with. OK, now we decrease this. This is amazing. From 7,000, it was 7,000 to 4,000, the error. OK, good. We are making some progress. And if you look at the loss function and the mean absolute error, you can see that it's decreasing, right? This is exactly what you are looking for, to decrease our loss function. Now, here the mean absolute error and the loss are overlapping because in our model, we are using the metric and the loss the same. So this is why we are having the same kind of graphs here. But just by looking to this, you're going to say, it's decreasing. Let's add some epochs. Maybe it's going to decrease more, right? If you look at these graphs. So you're going to take the same model, but this time, let's add 100 epoch. How are you going to perform? Let's see. We add, OK, it did well. From 4,000, the mean absolute error, to 3,000, you see? OK, so we were right. It's decreasing here, so we added some epochs, and it worked. Let's see to the loss function this time. Now you see that it starts to get in at the lowest level. OK, we have seen also that normalizing our data can get us better result when working with neural networks, right? Let's try to do this. For that, we have already a function for that, which is called min-max scalar. Let's see how we're going to perform when normalizing this time our data. So we're going to take the same thing. OK, I lost my resources from Ibex. OK, let's see if this one is still working. Just check. Yeah, this one is dead. And this one. Let me try to run it quickly. It's working. Okay, this one. Okay, we were here. Should be, let's see. All right. So again, we're going to take the same CSV files for the insurance. And this time, we're going to normalize this. So this is a small pipeline to do this. We're going to use the make column transformer for that. We're going to not only encode our categorical features, but scale in also the numerical one using the min-max scalar here for the age, the children, and the here, yeah, and the BMI. These three features. And these three, we're going to encode them into numbers, converting them into numbers. And let's fit this with the same model, right? We're going to create our X-train and X-test for that. And you can see an example of the X-train normalized and the encoded. This is a small example of one sample, and we convert it into something like this. The numerical one was now between 0 and 1, and the others are encoded. And let's see how our model is performing now. We're going to use the same model, but this time on data with with data normalized this time. Let's see how it's going to perform. Okay, it's going to take a little bit of time. All right, amazing. We gain 10% less error between the previous one and this one. So you can see that try always to normalize your data, always. You don't care. When you have some data, normalize it. It's going to give you a small, even if it's small gain, do it. You don't care. Do it all the time. Now, let's try the final example, which is an advanced one. You can see it here. We're going to use 256 neurons. Then you're going to use what we call dropout. It's a new layer here. It's to avoid overfitting. This is the kind of stuff that you can use. Then you're going to use another layer and do it again and again. So it's very advanced one here. You can see it. And we're going to fit it for 200 epochs. Let's see if you're going to perform well or not. So you can see it. As more you give layers, the calculation become more and more. And it's going to take a lot of time. OK, amazing. You see, by using a small, complicated one, an advanced one, we were able to get and reach 50% less error, from 3,000 to 1,700 for the mean absolute error. This is an example of how you can use neural networks for regression problems. This is a small example. Now here, I put you again some exercises if you want to practice by yourself using this time another kind of data, which is the California data set. You can practice by yourself using this, right? OK, we finished the first examples. Next one is classification. But before that, just want to show you something. I'm using a GPU, which is an 800 here. And if you look to the memory, you can see that's already full, right? You see? So now I'm not even able to get to the next one without resetting, doing a reset for my kernel. You see this kind of stuff when you're working with deep learning models, it gets very quick, like for the GPUs, it's very big. Now if I'm looking to it again, you can see that it's empty because I erased the kernel. And now I can proceed with the second examples, all right? This is small, quick, just to give you an idea. All right, we're gonna take a small break, 10, 15 minutes, and we're gonna finish with the two final examples. All right, see you. Just Okay. So the same thing. We're going to try to start with some synthetic data for the classification, and then we're going to go to some real data. For the synthetic data, let's see an example in order how to create this. We're going to try to create binary classification with synthetic data. Here, let me run this. Let's create our synthetic data. We're going to use what we call make circles provided by scikit-learn. And we're going to create our x and y. And you're going to see here that x is going to be represented by some coordinates, a position, y, and y by labels, 0 or 1. So two classes here. But again, this is why it's important to visualize every time. If you look at to the data frame, you're going to see it's equal to x0 and x1, which represent the coordinates, and the label. And we have 500 samples for class 1 and 500 samples for class 0. And if you visualize this, it's going to be like something like this. And we're going to try to build some neural networks to classify this kind of synthetic data, right? Let's see how our model is going to perform on this kind of synthetic data. So again, you're going to look at the shape. You can see that we have 1,000 samples for x and y. And if you look at small examples, you're going to find that it's representing the position for x and the class for the y. And let's start building our first model. Same thing. You remember for the regression? It looks exactly the same, right? We're going to have our hidden layer with 1 neurons. But small difference here, it's in the loss function. Before we were using mean absolute error. But now that we are working with a classification problem and binary one, which is 0 or 1, we're going to use binary cross entropy for the loss function. Optimizer is going to be the same. The matrix is going to change. We're going to use accuracy this time. And we're going to run our model for 5 epochs. Let's see how we're going to perform. Is he going to be able to classify this synthetic data or not? All right. Let's see. The results is not that good. You see the accuracy here? It's equal to 50%. It's like guessing. He's not learning very well, right? Even when I run it for 200 epochs, same accuracy, 50%. Okay. Let's add a new layer. Let's see, maybe he's going to learn better, right? We're going to add a new hidden layer here with 1 neurons. Going to use the same parameters. Let's see this model how going to perform. Are you going to perform? Okay. Now it starts getting 0.5, which means 50% accuracy. It's guessing. It's not doing anything. Not that good. Let's see. We have already seen how we can improve our model, right? And make it more complicated like this one. Okay, let's try this and see if you're going to be able to fix this. You're going to do this kind of model. 2 hidden layers with 100 neurons, 10 neurons. We're going to change the SGD, stochastic gradient descent, by the Adam one. We have seen that he's performing very good with the last previous examples. And we're going to use the binary cross entropy, of course. Let's see how our model perform, and for 100 epochs. Okay. You see the accuracy here. Even with a bigger model, still having 50%. We are missing something here, right? This is why visualizing things can get you some insight. Let's visualize this. Let's create a function for that to see what's going on, what he's doing. Okay, let's plot the prediction using our model. Okay, now we get an idea. He's doing a linear separation for our problem, which is not linear in our case. This is the missing thing, the non-linearity. You see, by just visualizing the thing, you get it. Now, the missing piece is the non-linearity. This is why it's important to also always visualize your results. Now here, there is this website, which I like a lot, which allows you to create your neural networks and get exactly the same kind of results. Let's see this. Okay, so here, this is exactly what we are building, right? We have x1 and x2 and 1 neurons. And if you run it for a lot of epochs, you can see that it's not performing well. 0.5, same thing, same accuracy. But it's in an interactive way, which is good to see, even after 2,000 epochs. Okay, now we know how to can play with this. But again, we are missing the nonlinearity. The idea here is that let's try to play with the activation function this time. You see, it's linear here. The activation function for this hidden layer, it's linear. This kind of model, it's exactly the same as this one. It's 1 neurons and 1 neurons for the prediction. This is what we are building. 1 neurons here and 1 neurons for the prediction. And we're going to use linear one. And you can see that it's not working. You see? Even for our model here, it's not working also. It's giving us 0.5. You see? This is just to give you an idea how you can visualize your model, how it looks like. I know that's a lot of code here, but to visualize it is doing exactly this. And we get exactly the same thing here. You see? 1 neurons and 1 neurons. If we change it to this, yeah, you see? We are getting the same results. Okay, now we get it. We are missing something, the nonlinearity, right? For that, same thing. If we change our activation, we have already seen this here with the rectified linear units. It's going to give you the same results, 0.5. Yeah, it's not learning anything. But now, let's try to build the same here. You see? So 4 neurons, 4 neurons, like this one. And let's see if you're going to converge on. Ah, OK. Now it's working. OK. Even for the sigmoid. All right. Now he's doing it, right? Let's try to build exactly the same thing and see if we can get the same results. The idea here is that we're going to do the same thing. So we have 4 neurons, exactly the same thing here, 4 neurons. But the activation function, we're going to use sigmoid. Let's see if we are able to get the same result as the website. We're on it for 150 epochs. OK, it's taking some time. Amazing, we get it. You see, now we have the same result as the here. This is what we were missing. The activation function. It was linear before. This is why we get this kind of stuff. He didn't learn anything. Why I'm telling you this? Because if you look at give you more insight about it, what he's doing when you give him some inputs, like the x here, and you give him some activation function which is linear, he's not learning anything. Why? Because you're going to get the same plot. If you give him this linear function, you're going to get the same results at the output. So he's not learning anything. But if you are using the sigmoid function, the activation one, it's going to do this kind of things on your data. It's going to change it to this function. So it's manipulating a little bit your data in order to gain some understanding and some new patterns. But if you give it, and same thing for rectified linear unit. If you give him a linear function and you apply the rectified linear function, it's going to give you a result like this. So he's changing your data, right? He can learn some stuff from that. But if you give him only a linear one, it's going to give you the same results, the same entry as output. So he's not learning anything. This is what we are missing. Okay, now we were able to resolve this, right? Let's evaluate this model. For that, again, same thing. We have 1,000. You're going to split this into some training and test split. We're going to take 80% for the training and 20 for the test. And then we're going to build our new model on that. And let's see how we're going to perform on the test set this time. Okay, you can see that 200 epochs. We are getting 99% accuracy. Amazing. And for the evaluation, so the accuracy on the test, we're getting also 99%. So he really learned how to separate these two classes. And you can see it here for the training and for the test. He missed maybe this one and this one, right? 2, which is nothing. So amazing. We have a good model here. Now, let's see the plot of each time when you are using deep learning models. Try always to look at the loss function. How is training? So you're going to have this function, which is called history. Again, don't worry about the codes. You can always get back to it. You have the everything. Just try to follow and understand the principle here. The code, it's nothing. You can practice by yourself again. So we're going to have what we call a function called history that gives you the loss and the accuracy of your training. And if you look at the curves, try always to look at your loss function and accuracy function. And this is exactly what you are looking for. Loss function to get very low and then accuracy to get very high. And you can see it here. It's doing beautiful. It's amazing. This is exactly the kind of stuff that you are looking when doing some deep learning models. All right. Now, another step to speed up the process is to find the best learning rate. Why? Because when you are looking and working with the big data, sometimes it's going to take you a lot of time to train on them, right? But if you find the best learning rate, it's going to accelerate this. This is a small example of it, how you can do it. Again, it's already a function provided by TensorFlow. You can use it, and you're going to test a lot of different learning rates for your optimizer here, the Adam, and it's going to give you some plots. I'm not going to run this, but you can see that it's going to take some time. But it's going to give you something like this, the loss, accuracy, and the learning rate. And if you separate this learning rate and you compare it to the loss function, only to the loss, you're going to see something like this. You're going to test a lot of learning rate, and you can see that the best ones are here, right? Because it's going to give you a small loss function. We are always looking to the smallest one. So here, you can see that the best learning rates are between 0.01 and 0.1 here, right? Now we have our best learning rate. You can use it now and build a model on it. And you can see that before we were using 200 epochs to get the results. Now just by using 25 and using the best learning rate, which is 0.05 here, because we have seen that it's looking here, it's going to accelerate the process. And just by 25 epochs, we get the same results, 95 accuracy. This is, again, kind of stuff to accelerate your process when working on this, looking to the best learning rate. All right, now we have our model, and he's performing very well, just by running for 25 epochs, which is nothing this time, not 200 epochs like before. Again, now we are working with synthetic data, so small data. This is why it's a little bit quick, but when you start working with real data, it's a different story. This is why it's important to look at the best learning rate. It's going to accelerate a lot of your models. Okay, now some more classification evaluation metrics. We have already seen this: the accuracy, precision, recall, performance score, and the confusion metrics. Let me just run this last model. So you're going to use it. Okay. Now, confusion matrix, it looks like something like this, with the true labels and the predicted labels. And here you're gonna find the correct one, so the true positive and true negative, and here, the false positive. This is important to look at to this kind of stuff, the confusion matrix. Again, it's proposed by scikit-learn, but you can see that if you apply this directly to the prediction using your model, it's gonna give you an error. Why? Because the prediction here, when you are predicting using your model, it's giving you some probabilities again. I told you, deep learning models gives you probabilities. So you need just to do, and you are trying to predict 0 or 1, right? Just to do a round to get the real class. And now you can build your confusion matrix. And you can see that's performing very well, right? And better look is this one. It's performing amazing. The true labels and the predicted one. All right, now we have C on static data, how it looks like. Let's try to run it on a real data. But this time, working on multi-class classification one and using images. Let's see how artificial neural networks perform on images. For that, we're gonna use what we call the fashion MNIST dataset. Again, you can download it here. I already did it. Let's get a look to this. It's a dataset that gives you, okay, let me try to run this. All right. It's a dataset that gives you 70,000 images of 10 classes. For each class, here we have done the split. You can see for the training, we're gonna use 60,000 images, and for the test, only 10,000. Okay, you can see it like this. For each class, we have 6,000 images and 1,000 to the test. But again, it's just numbers, so we wanna see some images, right? This is how it looks like. You're gonna have a lot of images that describe a lot of different type of clothes. But if you look at to the labels, you can see that it's number going from 0 to 9. We don't like this, so we know what we are trying to predict. This is the kind of class names. So we're gonna create a dictionary for it. We're gonna try to predict like t-shirts, trouser, dress, coat. We know this from the data set. So we're gonna replace our labels by these true names. And now we can get a better look with the name here. And we can create some functions to see a random images. So here it's t-shirt, but let's try another. Okay, you can see bag, pullover, t-shirt, t-shirt here. All right, sandal. So this is the kind of images that we are trying to predict this time. We have 10 classes. It's a multi-class classification problem, and we're gonna try to resolve it using this time artificial neural networks. Okay, let's build our model. For that, again, the shape gonna be 28 by 28. Why? It's the size of the image, and it's in grayscale. This is why we don't have the color channel, RGB. You can see it here. It's in grayscale. And we're gonna build four neurons, and for the last one, we're gonna put 10, because we wanna predict 10 classes. And here, this is the most important, it's softmax, because we are working with multi-class classification problem. If we were working with only binary one, we're gonna use the sigmoid one, not softmax. And here, we're gonna compile it using sparse categorical entropy and use the accuracy for 10 epochs. Let's see how we're gonna perform. You can see that now it's taking more time because we are working with 60,000 images for 10 epochs, okay? Now you can see it here for the accuracy, right? 45. Not that good, huh? Yeah, same. Okay, you see, not that good, huh? Working with artificial neural networks for images, 45, 46% accuracy. It's not that good. But remember something? When we were talking about images and deep learning, normalization can help you, right? Let's try this time to normalize our images. We know that our images, the mean and the max, are equal to 0 and 255. Let's try to normalize our data just by dividing it by the max, right? 255. And let's run the same model on normalized images. Let's see how our model is going to perform. Okay. From the first epoch, you can see that we get already 60%. Now 71. Okay, you see? Just by normalizing your data. This is why it's important. Try always to normalize your data, always. Especially when you are working with images. This is very important. Okay, you see the difference? Now we are around 80% accuracy for 10 classes just by normalizing our data. And you can see it here. This is very important. Try always to look at the loss function and accuracy. Again, we have the loss function and accuracy for the training, and for the validation. Doesn't look very good, but for the normalized data, it looks very good. This is what you are looking for. This to be very low, and this to get very high. This looks good. All right, amazing. So now we have seen, just by normalizing this, we get very good results. Now, again, you can always look at for the learning rate, the best one in order to improve it. I'm not gonna run this, it's gonna take a lot of time, but again, you're gonna just use this kind of function, the callback, and it's gonna give you the same kind of test a lot of learning rate, and it's gonna compare it to the loss function. And you can see that the best one are here, around here. And now you can do exactly the same thing, but this time using the best learning rate and reduce the epochs to 20, for example. And you're gonna get the same kind of results. You see, just by using the best learning rate, you are gaining some way, some time. And finally, let's try our advanced model. That looks like this. A lot of hidden layers and a lot of dropout to avoid overfitting. It's an advanced one with 500 and 200 neurons, a lot of, it's a very big one. Let's run it and see the different results. Let's see. You can see that from the first epoch, we're at 83%. But the problem with that, I'm not gonna run it again, it's gonna take you a lot of time when working with this. It's an advanced one, you see, it's a big one. And he's trying to predict 10 classes. And you get very good results, amazing, 87%, but it's gonna take you a lot of time. And if you look at the model summary, it's a huge one, total parameters, you see? 400,000 parameters, just to predict this. Again, here, I already save it, so I can load it again and do exactly the same thing in order to make the prediction. Now that you have our advanced models, so again, it's an advanced one, but it's gonna take you a lot of time to run it, for example. And if you look at the confusion matrix of this kind of models, this is why it's very good to look at the confusion matrix for the prediction. Here, I'm just predicting on the 10 classes to get my confusion matrix, which looks like this. All right. Here, why I'm telling you to look at always to the confusion matrix, because it's gonna give you some insight. Look at this. This is the true label, right? And this is the predicted one. If you look at the t-shirt, you're gonna see he's performing 81% correct, but 13% is getting wrong. But why? If you look at this, okay, makes sense. He's confusing t-shirt with shirt, which is okay, understandable by a human. Okay, I get it. I get it why he's getting wrong. Same thing. This is why it's very good and to look to the confusion matrix. Same thing for shirt. When he's predicting shirts, he's getting confused with t-shirt here, for example, for 11%. So try always to look at, when working with images, of course, to the confusion matrix. It's going to give you a better idea. All right, now we've resolved this. Let's run a small example to predict. We create our function to predict on test data it hasn't seen before. And it's performing very well. It's predicting code with a confidence of 94%. Let's try another one. Okay, sneakers win 100%. Another one, trouser with 100%. You see, he's very good at it. He learned. And we get an accuracy of 87%, right? But you see that the model was very big and it's gonna take you a lot of time for that. Next step is convolutional neural networks. Why I'm telling you this? Because it's very adapted. Let me just increase this. And optimized to work with images, the convolutional one. This is the kind of models that we are using when working with images. We don't use artificial neural networks. I'm just showing you how you can do it, but don't do it when working with images. Go with the convolutional neural networks. And this is a small model, and let's run it and see how it's gonna perform using, flatten. I need to import it, the flatten one. Check where did I import it? Okay, you see how it's fast? Just by running 10 epochs, it was very fast, and it was training on 60,000 images using convolutional networks. And we get 90% accuracy just by using convolutional networks. You see, the previous one was very big and it's gonna take you a lot of time, but here it's 1 second for each epoch, and we get 90% accuracy. This is amazing. This is what when we're working with images, always work with convolutional networks. All right, let's see the last examples for computer vision. Again, I need to restart the kernel because the GPU is. I put you here again some exercises that you can practice by yourself with other kind of data set. All right, let's see the final examples. Convolutional neural networks for computer vision. Here we're gonna try to resolve two inverse problems: a binary classification and multi-class classification for images. The first one, to predict if an image is a steak or pizza. And finally, we're gonna try to predict for different kind of foods, 10 classes, for example. All right, let's try to build this time, but this time using convolutional neural networks. And let's see how it's gonna perform and how we can maybe at the end create an app food to predict the images of the different kind of food. Let's see. So for that, you need to download this. Already downloaded for my case, I think. And the data look like this. We're gonna have some training folder, which contain pizza and stack folders for the training and for the test. Same thing. We follow every time this kind of architecture when working with images. 2 folders, train and test, and then you put the different classes that you wanna predict each time. Okay. Okay, he find the different faults, and this is the different images that I'm gonna use for that. But let's have a better vision of it. So again, we're going to use 750 images for the training and only 250 images for the test, which is nothing, right? Let's try to perform on this. So we have 750 for the training. We have our folders, pizza and stack. Let's visualize them. We create a function for that. This is the kind of images that we have, for example, for the pizza. Okay, you see, we have different shapes. You can notice this. It's not always the same shape. You see? Okay, we have an idea about the images that we are working on to predict the pizza. Then the image is gonna look like this. It's a matrix with RGB because we have 3 color channels. And the size is gonna be different for each image. The width and the height is different. All right, first step, working with images, we're gonna normalize this. Let's normalize it by dividing by 255. And let's see how our model gonna perform. Here, we're gonna use, this is, if you remember, this is the kind of architecture of convolutional networks. We're gonna use convolutional one, max pooling, convolutional layer, max pooling, then flatten all this into one layer, and then using a deep neural networks. Here, we're gonna start by an end-to-end example directly, using a very common one, and very common one and very used, tiny VGG, which looks like this. This is the architecture. But I like this website that explains very well. Let's see an example of it, who are gonna explain to us this tiny VGG. So as you can see here, let me just here. We're gonna try to apply this architecture. Okay, try to. It looks like the website. Oh, it's working well. Okay, it's loading. All right, this is the architecture of the tiny VGG that we're gonna try to implement here directly. You can see convolutional layer, max pooling, and again, and flatten and dense. What he's doing in reality, you have your RGB, so the image, the color channel, and for each one, you remember this is the first convolutional layer. What he's doing is just taking a filter. You can put a lot of filters here, as you wish, in order to gain some understanding of the image, maybe the textures or the edges. And you're gonna pass this into your image, right? In order to get the result here. So you're gonna do it for the for the red, green, and blue channel each time. Then when he gets this layer, he's gonna do activation function, right? The one that you have seen layer, rectified linear function. So for each pixel, he's gonna pass it through the max between 0 and the value. So if it's more than 0, you're gonna put this value, and if it's under, you're gonna put 0. You see? Okay, this is exactly what he's doing for each image. Then you're gonna do exactly the same thing. These results, pass it through another convolutional layer. And you're gonna use different filters and go through the different image, you see? Again and again, in order to get the results. After this, activation function. You see how it's big. Okay, he gets some new image. What he's gonna do? A max pooling, which means just reducing the size. From, for example, 60 by 60 to 30 by 30. You see how he's doing it? For each pixels, he's taking the max pooling. And we get a new one, but a reduced size of our image. And you're gonna repeat this. New convolutional layer, rectified, linear, then max pooling, and then finally, you're gonna try to predict here, as you see, the different classes. Is this image representing school bus, pizza. You see, this is how a convolutional neural networks works. And this is exactly what you are building here. As you can see, this architecture is given you here by this code. But this time we are trying to do it only for two classes, pizza or stack. Let's see how it's going to perform. So we have our images that belongs to two classes for the training and for the test. And you can see that this architecture is very good. It's performing very well just by doing it for 5 epochs. We are getting 85%, which is amazing, knowing that we are working with small data sets. 1,000 images is nothing when working with real data. It's nothing. So if you look at this, very interesting, because if you look at the model summary, you're going to see that it's using 30,000 parameters. Why I'm telling you this? This is very important. And this is why convolutional neural networks is very powerful when working with images. If we take the same model as before, the one that used artificial neural networks, this one, if you apply it to this kind of images, you're going to see that it's not going to perform very well. OK, it's just 0.5. It's guessing, nothing. OK, we get it. But let's try the advanced one that performed very well, right? The 87% accuracy. Why I'm telling you this? Because if you look at to the model summary here, you're going to see that this small one that performs 0.5 are using 600 parameters compared to the convolutional one that used only 30,000 and perform at 90%. Why it's important? Because look at the next examples. Let's use this model. You remember the one advanced one that gave us very good results. If you apply it, let's see how we're going to perform on this kind of data. OK, good for us. So it's using 75%. OK, good. Amazing. Remember, the convolutional one was around 85 for this kind of data. OK, if you look at to the model summary, even if he's performing very good, you're going to see that he's using 20 million parameters in order to get this kind of result of 70%. Or you see the difference when working with convolutional neural networks? Just by using convolutional networks that use only 30,000 parameters, you get better results than using one with 20 million. And this is very important why I'm showing you this. Because when you're going to start using deep learnings, the number of parameters is very important because you don't have enough memories on the GPUs. You cannot fit a lot of data on this. So this is very important. This is why convolutional networks is very important when we're working with images. You see the difference here, even if you get the same result using artificial neural networks, but you are using 20 millions. Yeah, this is the difference. Now, you can always break it down and give you all the steps again and again, going through the whole thing. So we're going to look at the images. We have these kind of images. You're going to do the pre-processing thing, train, test, normalizing again, then creating some batch size of our training, and do it again and again here, for example, to rescale, and create your model. Same thing, but this time we are using convolutional networks. Before, it was TinyVGG. Let's see how, if you can get closer to this one by our own model, how we can perform a little bit like him. And here, if you look at to this, let's see how we're going to perform using this, our own model here, which is just convolutional layer, 3 convolutional layer, and 1 flattened to flatten the whole data. OK, we are getting closer. We are at 83%. And if you evaluate this, all right, OK, you see the the curves here, you can see that he's doing a little bit overfitting, which is not that good. So let's try to make it better. Yeah, you can see it here for the training loss, validation loss, and the training and validation accuracy. For the training, he's performing very well, and for the validation, not that well. So maybe it's a little bit overfitting. He's doing some overfitting. Same here. For the training, he's performing very well, but for the validation, not that good. So for me, it's an overfitting here. To avoid this, let's adjust our models by adding max pooling, which means reducing the size in order not to learn a lot our data without to avoid the overfitting. Let's add some max pooling layer. Okay. Let's see how he's gonna perform. Okay. 83%, T5. Okay, 84%, which is good for me. But let's see the curve this time. This is the kind of curve that you are looking to. This, for me, is better than the other one. The other one, it's like it was doing some overfitting on this. But this one is very good. The both are following the same kind of, you can see it here. This is the kind of curves that we are looking for. All right. Now, we can do even better and create a new data set with data augmentation by doing some stuff on our images in order to make it difficult for our model to learn better. So for that, we're going to use image generator here. It's a function. And you're going to do some rotating, shifting, zooming on the data, and make it more complicated for the model to learn, which is exactly the real thing when you are taking the photo with your phone, for example. Sometimes it's not good. The quality is not that good. So if you make it more complicated for the model, we're going to get more robust one. And I'm going to give him this kind of images. Instead of original one like this, we're going to complicate it for it. Let's see another examples. You see, the guys was moving, for example. You're going to try to complicate it for the model. Like this one. And let's fit our model on it. You can see that now it's taking longer and he's performing less. But it's okay, because we are trying to get something that works in real world. So even if we are complicating this, it's good for us. But it's not performing very well, right? You can see it here. And it starts taking, 13 seconds. Okay, but the problem here is that when we were working with data augmentation, we missed parameters here, which is shuffle. It's false. And I did it in purpose to give you an insight about it. Never forget to shuffle your data. Put it always true. Don't forget. Otherwise, it's not going to perform very well. It's not going to shuffle your images. You're going to always use the same kind of images. You need to shuffle them in order to make it better for the model. This is why it's not performing very well. Now, if we take the same models and we do the shuffling, you're going to see that you're going to perform better. Okay. But you see that it starts getting, you see, 73%. Just by shuffling your data. Don't forget this. All right. Let's see. 80%. Okay. This is good. And now I'm using a GPU which is 800. Don't forget that. The most amazing one here in cost on IPEX, the A100, the most powerful one. And you see how it's gonna take time just by using some training images, which is nothing. You see how it's can get very, very exhausting when working with the big data. Okay, now it looks good. We have 86%. The idea is that you can always keep repeating this until satisfying. Trying, doing again and again, playing with the parameters again, again, again. But let's take it to the next step, which is transfer learning. Instead of going through the whole thing and using tiny VGG, for example, let's try this time to run a transfer learning on this. An advanced one that was already pre-trained on the huge amount of images. So we're going to use MobileNet for that. Let's try to run it on our model and see how it's going to perform. You're going to download the models, the pre-trained one. So again, we are using a pre-trained one and tune it and adapt it to our problems. And you can see that just from the first epochs, we get 98% accuracy. Amazing. This is why transfer learning is very, very, very important, valuable when you have some pre-trained models. It's going to save you a lot of in time and in money, because sometimes you're going to pay to do this training. Here we have our cluster. It's amazing. But in reality, people pay for that to get some cloud resources. So transfer learning is amazing. You see, just by running this on 5 epochs, we get an accuracy of 98%. Compared to the other one, you see, we have did a lot of stuff and getting and doing a lot of models. And here, just by using already pre-trained one, you get an amazing accuracy. Okay. And the curve looks very good. And you can save the model and load it again and evaluate it. You see, 97% on the test set. Amazing. Before we were at 87. Here, just by using transfer learning, we take it to the next level. And again, here, you can make a function, just to show you how you can do it, that do the prediction using these kind of models. I created a function for that. The prediction is not going to work here. This one, yeah. Now you can predict using this transfer learning model on the images that it hasn't seen before. And you can see that the prediction is very good. But you can take it again to the next level by using Gradio, which is a library that allows you to create some small dashboard, interactive one, that works very well, either inside your Jupyter notebooks, or it's going to give you a small link that you can share. Again, it's going to work inside your Jupyter notebooks. It's loading, or you can share it to your colleagues. And now you can test it. Let's test. And make it interactive, a small app. You can submit this. It's going to give you the confidence. All right, 100% pizza. You see? You can do it for stack images, for example, because it was trained on stack and pizza. And here, it's uploading this. It's predicting 100%, so it's very good at prediction. And you can create something like this, you see, just by using Gradio. But it's gonna, you're gonna share, the link is gonna expire in 72 hours, right? This is for you. We're gonna see later how we can do it in the last course using your own dashboard, which is Streamlit. You're going to see a small example of it here. This is just to get a small, quick one that you can share with your colleagues. But again, here, final example is multi-class classification. Again, you can always go through these different steps and doing the same thing and playing with the models and trying and again and again and again, or just taking it to the next level using a pre-trained one using transfer learning, the same model. So again, here, I'm going to go through the different steps again and again. But at the end, you're going to repeat this until satisfied. You can try the transfer learning, and you're going to see that by just using the transfer learning for 10 classes, which is a difficult problem to resolve, you're going to get an 85% accuracy by using transfer learning. So it's very important. Again, transfer learning, if you have some pre-trained models that look exactly at the same problems that you are working on, go for it. Go for the transfer learning. It's going to save you a lot of time. And finally, you can create what I called a small app. Again, you can do it for Gradio here. You can see it. But you can create something like this using a library called Streamlit. Let's see this. Okay, it's taking time. It messed up this. Restart the kernel. Maybe it's GPU is not. Okay, it's going to give you some links. And here, you can really share it with your colleagues because it's running locally on your machine. It's not like Gradio. Gradio is working on their own web server. But this Streamlit is running on my local machine. And you can share it. And it's going to look like something like this one. A small app that you can share with your colleagues to train new classifier, for example, or already use the pre-trained one that you have already seen. And you can upload your images, but this time, the model was trained on 10 classes, right? And you can see it by trying to predict if it's Solomon or not. So it's upload, and it's predicting with 94% accuracy and confidence. It's saying that it's great Solomon, you see? And here you have an app food that detects the different kind of foods from these 10 classes. And you can try it again with, for example, I don't know, chicken wings. Let's see if you're gonna be able to predict this. Okay, you see, 98% he's predicting it's chicken wings. Final example, I don't know, hamburger, let's see. Okay, 99%, so it's amazing. So it's doing very good. And this is that kind of app and dashboard that you can build and run on your own local machine and share it with your colleagues. And that's it off for today. I know it's a lot to digest, but again, the idea is just to give you an overview and an idea of what is deep learning and different kind of stuff that you can do. And again, you need to practice by yourself, and you have a lot of exercises, and you can get back to the Jupyter notebooks. And thank you. Thank you. Thanks. Thank you. Let's start this.